Hi guys, Neil Moss again. Want to talk to you about Unit 77, heat treatment of steel. Um, it's kind of, once again, textbooks don't do a great job of explaining this stuff, but they aren't very sequential in what they do. I'm going to change it up a little bit, making it hopefully a little bit easier to understand. They start off talking about the heat treat equipment and so forth and the ovens. It doesn't really matter how you heat something up. They have a climate control to them. Some of them have the ability to put in gases, and some of those gases will impart different properties to the outside of the steel. And actually, they can add carbon to the steel and so forth. But the ovens, there's a couple. There's a high temperature oven that's normally used to heat the steel up to higher temperatures, around 2,000 degrees. You got your low temperature furnace, which is used for to temper steel and so forth, and goes up to about 700 degrees Celsius or so. And then you might have a pot type furnace, which is used for liquid media, well, or molten media, I should say. Lead and salt are commonly used, as they mention in the book. But once again, yeah, the biggest thing is that they have the ability to regulate the temperature to a fairly high degree. And that way that's achieved is through a unit called a thermocouple. All a thermocouple is two dissimilar wires that are twisted at the end where you want to take a temperature reading, and it goes back to what's called a pyrometer. And what that does is that registers the voltage that's created at that point, and it converts it into either a digital or an analog scale that will tell you the actual temperature of what you're reading. Okay, well, that's kind of enough said about that. Um, the They go through a lot of heat treatment terms and so forth, and that's where that's the point of my video today. Is It's funny they call it heat treatment. You know what? It could almost be called cold treatment because it really doesn't matter um, the heat, how long it takes you to get there to the temperature and so forth. But what happens is when you cool it and how you cool it. So if you cool something, you heat it up and you cool it slowly, then it does what's called an anneal or a full anneal. If you leave it in the oven, turn the oven off, and if you're up a high enough temperature, it'll soften the metal back to its original state. But if you cool it quickly, it hardens the metal if it has enough carbon in it. Now, the percentage of carbon is very important in the steel. So we often talk about points of carbon, and it's at 3 points of carbon. It's percentage of carbon. Below that 0.3, you can't appreciably harden the steel. It won't harden. It's a mild steel. Unless you can impart carbon into it, if you put the carbon into it, then you can heat treat it. And there are techniques, a way of adding carbon to the surface of materials, mild steel. For instance, if you have a shaft and you have a large shaft, maybe it's 4-inch diameter, 10 feet long, and you have a bearing or a gear that you want running on a hardened surface, well, you can harden that outer surface by the addition of putting carbon into it. And you heat it up and you let it soak, and it's the longer you heat it up at higher temperatures, the further it'll soak in. And so it can actually sink in a fairly significant amount. And once again, the carbon can move, it's a solid, and the steel is a solid. So carbon moves around within steel as a solid form. It's red hot, everything is hot, but the carbon can actually move in the steel. And that's a very interesting fact sort of thing. But okay, let's start with this. So let me go through some of these terms with you and see if we can make some sense of it. Um, I'm not going to talk about the decoalescent point or the recoalescence points right now. We have what's called the lower critical temperature point. That's the lowest temperature at which steel may be quenched in order to harden it. Well, once again, you got to have enough carbon in the steel to harden it in the first place. But let's take a look at that, what it looks like on a graph. Behind me I got a nice whiteboard, and let's start with our graph. Okay, on the one range we have temperature, and that's our important one right now, your temperature. And now for all iron and steel, the basic lower critical point is at, I just want to make sure because it is changes from different textbooks from 720. Um, 723. 723. 723 degrees Celsius. Okay, that is your lower critical temperature. Now, your upper critical, and this is at a low carbon point, is a maximum of 910 degrees. And this would be your upper critical. And your lower critical. Now, the critical range is in between here. So this is your critical range. Now, if you're below that 723 degrees Celsius, you can heat things up and cool it, and you're not going to affect change to that at all. That's very important to note. So as long as you're above 723 degrees and you bring it up to that temperature and you cool it quickly and you have more than 3 points of carbon in the steel, you're fine. You'll be able to harden it. And that's the point I'm trying to get at. Another interesting point is the point just above the 723. That's called the Curie point. Now above the Curie point, the steel is no longer magnetic. And that's how the ancient blacksmiths and so forth, that's about 760 degrees. Say 760. Now the Curie point, where steel is no longer magnetic, the ancient Japanese sword makers somehow realized this. So they would have a piece of magnetic rock, and as they're heating up the swords, they would be touching the magnetic rock. When it no longer stuck to the steel, they knew that they could quench it and they could harden that steel. So that Curie point is very, very important to realize. And you can do this at home with a magnet. So if you're heat treating something and you wanted to find out, because you don't have the temperature sticks and so forth, which melt at certain temperatures, you can check it with a magnet. And it's very, very interesting. Well, it's interesting to know that all metals, the way they work and the way they join together is they share electrons. You've got a single atom of something, an individual atom, and around it, it's got its nucleus, and it's got electrons flowing around. And actually, they're out quite a ways, and I don't do it justice. But metals share atoms, and that's how they're held together. You get something that's a plastic or a rock or anything else, and they're sort of glued together. But they call it metallic bonding with atoms. Well, there's 7 different structures that I'm not going to get into that metals will form and so forth. Different types of metals have different structures. Well, the one we're worried about is the cubic structure, which is a square. The cubic structure, I'll just do it over here. The cubic structure is basically this structure. Now, we can arrange the atoms And there's an atom at each corner of a cubic structure. And each point has an atom where they're connected. You get the idea. Well, I've made a rendition at that. At lower temperatures, we have a cubic structure, and this cubic structure has your 8 atoms on the corners, and it has one in the very center. One in the center of that is the cubic structure. That's called a body-centered cubic structure, and that's the structure that steel and iron have. Okay, fair enough. This is at room temperature. As you heat it up, the metal up above that 723 degrees, I should mention above 910 degrees, it has this other structure which is called face-centered cubic. It doesn't have one in the center, but it has one on each face. So each face has 5. And you look at those and they share, and they're held together by the sharing of electrons in these cubic structures. And that's at elevated temperatures, above 910 degrees Celsius. Okay, room temperature, body-centered cubic. 910 and up, face-centered cubic structure. In between, in the critical range, these things coexist. So as you cool the metal down, this structure starts turning into this structure. And as you get closer to the 723, there's more of these and less of these. And this is cooling very slowly. So you've got a mixture in here, and pretty soon there's more of these, and until you get below this line, this doesn't exist anymore, and all you have is your body-centered cubic structure. Okay, now you're thinking to yourself, wait a sec, you've got more atoms in this structure than you have in this structure. And you're absolutely right. What happens to the extra atoms? Good point. The extra atoms form other structures in between these cubic structures. And these are called the grain boundaries. Okay, in these grain boundaries, you're going to get different structures, and they're going to have ferrites, cementite, and so forth, and perlite. And what they are is layers of different structures. Fair enough. That's how that works. So the extra atoms form this other structure. Now, in a nutshell, what happens at the lower temperature, we assume this is a carbon atom. Well, the carbon atom can't fit in here. It's just slightly bigger, and it pops out at cold temp. So essentially, you can hold 0 carbon in this structure. But at elevated temperatures, one, because the temperature is hotter, so the atoms are more excited, and there's a bigger space, well, the carbon atom can fit in the hole in the center of these. But as you cool it down slowly, these pop out. They can't go into this structure very much, and they keep popping out and popping up. And so the carbon with the extra atoms form these different structures, depending on the amount of carbon that you have in the steel itself. Okay, so hopefully that's not too confusing, but the premise of it is that's cooling slow, the carbon pops out. Well, when you're heat treating something, as we know, like a file or whatever, we heat it up, the carbon atom is inside that. If we cool it quickly, boom, it's locked in there. Well, with the carbon locked in this cubic structure at room temperature, it's under a lot of stress. It wants to break out. And what happens with that is the metal becomes very, very brittle, usually, and very hard. Well, without further heat treatment, that will crack, or it might have cracked already if you quenched it, if it's a very high carbon steel. The point is that we have to do other work to it or relieve some of that stress. What we do is we put energy in, and that's called tempering. So we'll heat it up to a range of 3, 4, 500 degrees. And it's below the lower critical. That allows some of the carbon to escape. And we cool it slowly. So it takes a little bit of the hardness away, but it makes the steel tougher. The higher the temperature that you raise it, the more carbon escapes and the softer it gets. So it becomes perhaps tougher, but it's losing the hardness, and it's losing more hardness as you get warmer and warmer below the lower critical. Interesting enough. And that's how that works. And there's a lot of different processes that we can do to steel and to play with that carbon within the steel. Now you got to remember, the steel is a solid all through this. It's just red hot. It gets red hot, but it's still a solid. And the carbon is allowed to move, but it does take some time. So when you heat treat something, you're heating it up and you're leaving it soak for about a half hour per inch of material, and you let it soak at that temperature. You don't want to leave it soaking for too long because you want to have what's called a fine grain structure. Now, the longer you leave it at that temperature, it gets to be a coarser or a bigger grain structure, and you prefer a finer grain structure in most cases. So I hope that gives you a little bit more understanding about that. Now let's try something else as well. This is at one specific point of carbon content, and that's just for a show sort of thing. Now let's kind of look at the structure of a proper structure of carbon in steel. Okay, I'm going to redraw my graph. Let's try red this time. Once again, we have temperature. Your temperature going up. We started at 723. And over here, we're going to have percentage carbon. This is going to be percent carbon content of the steel. Okay, we start at 0, and we can go up. Now, one of the most critical points is 0.81% or 81 points of carbon in the steel. Once we get up to 2%, it's no longer steel. It becomes cast iron. The reason that is because this can hold 2% carbon by weight. Once it goes beyond the 2%, it becomes cast iron. So from 2% on, it's cast iron. Keep that in mind. So maximum carbon content of steel is 2%. Okay, so remember I mentioned that 910 degrees Celsius. As you add carbon, to the steel, the melting temperature does go down. 723 is straight across for all iron. That's the lower critical for all. It doesn't change. But this upper critical, in our last drawing, was straight across. But now, because of different carbon contents, it goes down. And then it will rise again as such. Once again, up here, we have our face-centered cubic structure. Lower temperature, we have our body-centered cubic structure. In between here is a mixture. These two are mixed. And as we cool it slowly, we get more and more body-centered cubic unless we cool it quickly. We cool it quickly, boom. It just locks it in there and the carbon is stuck in there. And that's the whole premise of this. That's really important to know. So this is lower critical, upper critical, and then you have your, once again, your curry point. Now, you see these pictures that they have of the, on page 663, of the different perlite grain structures and so forth. Sorry, my other camera's not working, but this structure here. And what happens is that you're looking at a structure looks something like this. Odd shaped or whatever, grain structure, and it has lines through it and so forth. You got lines. Well, what you do is they etch that. They pour acid on the steel specimen. You put acid on it. The dark lines are the valleys. The white that you see is the hard spots. So you have structures in there, and you have cementite and so forth, which is a very hard structure. The ferrite, not so much, and cementite. The reason is because the softer material gets eaten by the acid, and when you look at that, it appears darker. Well, you may ask, why does that appear darker? Well, the reason some of the lines appear darker is because if we were to look at it, and this is your eyes, you're looking down at a piece of metal, and it's never flat, or it's looking, and you have sunlight coming down on this, rays of sun. The light goes down. If it hits a peak, it bounces up. That would appear as a black line. If it comes and it hits the point of a peak, comes up and hits your eye, that's a white line. And that's how you get the difference in white and dark lines in that. So that's just sort of an interesting fun fact on that. So what have we learned on this? Well, the baseline of the lower critical point is 723 degrees Celsius. The maximum is 910 degrees Celsius. Now the curry point is around 758 or 760 degrees Celsius. So what happens, it's where it's no longer magnetic. And that's how you can know you can affect change to the steel by heating it and quenching it at that point. So that sort of takes care of things in a nutshell. But one other thing that they talk about, and they do their drawing, and they have these plateaus when you're heating steel and so forth. Well, let's talk about water for a minute, and I think they mentioned that in there. If you have water, another graph, and we're going to talk about H2O, and we are going to have 0 degrees. Below this, it's ice. At 0 degrees, that's a solid. So we have our ice at 0 degrees. That's solid. As we heat this up, and I actually should have started, let's go minus 10 degrees Celsius. It's solid. As I heat this up to 0 degrees, nothing happens. At this point, it starts to melt. At 0 degrees Celsius, it starts to melt. We all know that. And it's turning into water. It's going to remain at 0 degrees. We're putting energy in this, and this is our time scale at the bottom. So we're putting energy into this, but the temperature doesn't change. Interesting. Until all the water has become a liquid from the solid, from ice. Until it all turns into water or liquid. It goes up. And our next one is what, 100 degrees? 100 degrees Celsius. It gets up to that 100 degrees Celsius. Once again, it plateaus there until all the liquid is turned into a vapor or steam. But it holds that 100 degrees Celsius as long as there's liquid present. Once it all turns into a vapor, then it can get higher temperatures. These plateaus these flat spots are called hysteresis. Hysteresis. What happens with hysteresis is that when you're going through a change of state, until everything has changed states, the temperature won't change. And that happens when we're doing steel making and so forth. That's why we have the time at temperature, or time at soak they call it, for different heat treatments and that. So you have to get it, allow it to change its state, and then go on from there. So very interesting points on that. Incidentally, the decoalescence point is the magnetic point, where the Curie point, where at 760 degrees, where the steel is no longer magnetic. The recoalescence point is just slightly below that because you're cooling it down, and that's when the steel becomes magnetic again. And that's due to this hysteresis effect in the change. That's shows you that drawing on page 662, figure 77/7. So that works out really, really well. They talk about Metcalfes experiments. What they talk about is the hardenability of steel. The hardenability of steel, wow. Well, all that's talking about, depending on the type of steel you have and the additives you have in it, when you take a piece of steel, if you've got a slender, thin piece of steel, and you quench it, you drop it in the water. Not a big deal. That goes in the water. Boom. You cool it down. It cools all the way through. It's not a problem. But if you take a bigger piece of steel, and you drop it into the water, obviously it's going to be a bigger tub. What happens is that only the outside of the steel gets quenched. So the quench is only on the outside of the steel. So it's cooled down, you've got a hard outside surface, but the inside is soft. You don't want that usually. What happens with that is you have what's called disbondment, it'll break away from it and so forth. So what we have to do is design steel by putting additives in it so that the piece can be thoroughly quenched and it'll be homogeneous throughout the whole body of that steel piece. You want it all the same throughout the whole width inside. And that's one of the biggest problems. So when you put enough additives in the steel, and they talk about the different additives that you can add to the steel. If you put enough additives in the steel, you can have what's called air quench steel. Now, we do use a lot of air quench tools. In the machine shop, the high-speed tool bits that we use, they're air quenched. You don't have to stick them in the water to make them warm. If you do any woodworking and you have a wood lathe, the wood lathe tools, they're very expensive. That type of steel is very expensive. They're air quenched because as you're cutting with the wood, the tool bit heats up, and if it doesn't stay hard, you'll just be sharpening it all the time. Well, they're air quenched tools, so it's very it's expensive, but you know what? In a lot of cases, it's worth it. They talk about, and this is the hardenability of steel. Now, the way they check that is a thing called Metcalfes Experiment. So you have a round shaft. Actually, I'm going to draw this up and down. And there's certain parameters for this. And you've cut notches in it. You machine notches in this steel. Very interesting. Wish we could do this in the lab. Unfortunately, you can't. We spray water on the bottom. You have a spray of water that comes up and cools, quenches the bottom of this. Well, it cools it down, but the heat has to transfer through the steel itself. That is it's slower. It takes a long time for the heat to transfer through. So this tells you how deep you can harden the steel. Once it's cooled down, you can actually take hardness tests and you'll see what the hardness is as you approach. And this would be soft, a lot softer than it is where it quenched here. So you do a hardness test on that, and that will tell you the hardness of it. You can also break the segments apart and look at the grain structure. Now remember, you prefer to have a finer grain structure, makes for a harder steel. But like I said, when we get into that, it's a whole lot of theory and so forth in that type, which is beyond the scope of this. You can read about the tempering colors. Then they talk about annealing steel. Well, once again, that's heating it up to above the upper critical point, above the 910 degrees in low carbon steel, and or whatever we have on our chart, and we let it cool in the oven. That's a full anneal. There is a lot of processes that we can do. And I also mentioned hardening the outside surface of a shaft. Well, if you want to harden something that's a low carbon steel or a mild steel, you can put it in a box and you fill it with carbon. Fill it up with carbon in the box, put a lid on it, and put it in the oven and heat it up into your upper critical range and let it sit there for hours. What happens, the carbon soaks into the steel and it becomes a higher carbon steel. There's also products, Casenite is one of them, where you actually just have a powder, you heat the steel up red hot, and you put, or until it's no longer magnetic, and you roll it in the powder or cover it with the powder, it lets it soak in. It soaks in a very small amount, but it's usually enough to make a big difference in it. And what happens is that then you can heat treat that area, you can quench it, and you can make a very hard surface if you have a shaft, and it might be a large shaft, and you're only worried about one area in here that a bearing rides on or so forth. So you want to harden one area, and you can use something like a Casenite product and so forth. So there are also Rather than pack carburizing, you have a carbon nitrating project where you can have the climate controlled oven and you put in a gas where the gas becomes with the heat and on the surface of the steel, it actually forms carbon and it soaks into into the steel as well. The longer you leave it in that oven in that state, the longer the deeper the carbon will soak into the steel. And that's carbon nitrating process. Cyaniding is another one where it's a liquid carbon nitrating. They're in liquid cyanide, which they don't let us use anymore. Now, you guys have all seen the gold drill bits that you can buy at Canadian Tire. The gold surface on that is a nitrating process where they actually put a very thin coating on it using the same sort of principle, and that's more of an external coating where it makes the steel very hard on the outside, makes it slippery, something like putting Teflon on a frying pan. Think of it along those lines, but it's very thin. They have induction hardening, and what induction is much like a microwave, but it induces heat into the steel, and it just doesn't matter how you heat it. Same thing with a torch. You can heat things up with a torch, and once again, and quench them, and you could harden surfaces, and that's commonly used in industry. I hope that answers a lot of your questions. If not, please send me a text or let me know, and I can address those issues. Okay, thanks for listening in.